let's try and finish off with polynomials and their relationship with containers. I'm hoping that on Friday, we've been looking at data structures. Let's start to look at data structures for the particular use case of representing the syntax of programming languages. If you wanted to use this programming language to build another programming language, what would you do? How would you do it? That's where we're going. But let's finish this off. We were looking at polynomials. Where have I hidden them? Which are built from variables, constants that are either 0 or 1, addition and multiplication, and we interpreted them as types. And what I wanted to show you was that I'd basically just written down containers differently. So what I was doing last time, where have I hidden it? I was, for the special case of polynomials in one variable, showing you how a polynomial gives rise to a container which has one sort of node and one sort of position for substructures. And I had got, so how do we give a container? We think of the index, in this case the index is not very exciting, as telling us the perimeter or the if you like, the rule, the thing we've got to fit with. And then we say, we give the ways of cutting up the perimeter, or otherwise, the ways to make a node. And then we say, given the way we've chosen to make the node, what are the, what's the list of positions for substructures? And then you give the actual data by choosing one of the available cuts, and you have to give pieces, you have to give substructures for all of the positions. So what happened with polynomials, we have to give, we have to say, what are the ways to cut things up, and what are the positions? And we got part of the way. We said that the ways, the possible node structures are given by evaluating the polynomial at 1. So what does that mean? That means that you have chosen a node structure, but you have uninformative stubs in all of the positions for data. And now what we have to do in order to give the positions is to give the list of those stubs, effectively. So what happened, in the case where the polynomial is a variable, that means there's a position. So we give the singleton list with one, saying there's one position here. If the polynomial is a constant, that means there's no position, so we give the empty list. If the polynomial offers us a choice, then we've got some work to do. You can see that our shape information is either a P or a Q. So if we see which, so in the case where we get a P, we can say what are what are the inners? Maybe it's going to barf at me, which would be annoying. Better open this record. Oh dear. Now I've really broken things. What's its problem? Maybe I'm undoing it. What have I done with this? I've just put the brackets in the wrong place. Right, so what am I saying here? We look at the shape, it's either a P or a Q. If it's a P, we say what are the positions inside it. The same thing happens if it's a Q. Now, the key question is, what happens if the polynomial is a pair? What are the positions inside a pair? Well, they're either positions on the left or they're positions on the right. So we better collect them all. So what's happened? What are these things anyway? You know when you have a polynomial expressed any way you like in terms of multiplication and addition, that you can, if you want, multiply it out, so that you've got all the pluses on the outside and all of the terms are products of variables with a coefficient. So you've got, so that you've got it into the form of a sum of products. If you've got any terms which are products of sums, you can multiply them all. So what we're saying here is that we are computing the sum of products form of the polynomial. These lists that we're building here are just lists of the variables. We're saying, you have these choices of how to build a node, and depending on which choice you make, you have, well, a list of elements of 1. A list of elements of 1 is otherwise known as a number. The nil behaves a lot like 0, and cons of the empty tuple behaves a lot like successor. So what we're really saying is, this tells us the shape, and this tells us the size. be slightly more daring, but not much, by saying if we have a polynomial in I variables, then we have positions that are labeled by elements of I. So now instead of saying our structure packs up only one sort of substructure, we're saying there's a whole bunch of substructures that we're packing up, different sorts of substructure, and we can pack all of those things up. So let's, all we have to do, this will now be an element of I, all we have to do is record which sort of substructure was in each position. So all we're doing is making a big list of all of the variables that occur in polynomials. Okay, so we've now seen two different variations on the theme of descriptions of data structures. We've seen containers, and we've seen polynomials, and we've seen just now that the polynomials are really, the polynomials give rise to containers, that the containers are a particularly normalized form of polynomial. What I wanted to do before I move on, I'm grateful to past me for writing some of this. I'm going to stick a question mark in there. Is we've so far looked at polynomials only in one variable. So what we say up here, the data structure given by a polynomial, what do we do? How do you build a node? You evaluate the polynomial, interpreting the variables as recursive substructures. And that allowed us to build things like NAT, where we said you either have a 0 or a successor with a position for the number one smaller. We were able to build binary trees. But what if we wanted to build something like lists? Remember, our language of polynomials only has constants, which are 0 or 1. How could we say that lists have elements? If you think about what's in the nodes of a list, there's two sorts of stuff inside a list node. There's two sorts of stuff inside a cons. There's a head and a tail. That's to say, on the one hand, there are substructures which are elements, and on the other hand, there are substructures which are sublists. So what's going on in the general case is that we work with two sorts of stuff in data structures. If we're building recursive data structures, we have to think about what the recursive structure of the data might be, and we also have to think about the elements that we store in the data. So what does that mean that we need? We're going to have some sorts of elements. Maybe like lists, there's only one sort of element in a given. Once you choose the element type, that's the only sort of element, but there might be more. We might be picky about which elements we want in some way. And there are going to be some sorts of nodes, right? Remember vectors. There's the node structures are given by the natural numbers. The natural number tells you the length of the vector. And what kind of stuff is stored in a vector node depends on that length. So we've got different sorts of elements, we've got different sorts of node. How, in general, do we characterize a data structure? Well, for each sort of node, we need to know the polynomial that describes those nodes. And fortunately, we get to look at the sort of node we want before we have to say how to build them. What sort of stuff gets stored in nodes, or in the positions? Well, they're either elements or substructures. So if we have a polynomial whose variables tell us, what goes here is either an element of this sort or a substructure of that sort, we've got it covered. Then to build the whole thing, we'll need to know how to interpret the element sorts as sets. That's going to tell us, this is where we plug in the element type. And lastly, we need to know which sort is the sort of the top node. So if we're building a vector, we need to know how long. So we have to pick one of our sorts of structures as the sort we start with. Okay. Then how do we build this lump of data? So F determines the node structures, X determines what the elements are, J tells us the sort of the top node. So we're going to have to find the polynomial that describes the top node. And we just said that's given by applying our function to the sort of the top node. So f of j is the polynomial that gets chosen by this little j. That's the sort of the top node. Now we have to say how to interpret the variables. So what do we have to do? We have to give a function that says, when you see something, when you see a variable, the variable tells you what goes here. And we have to say what set is meant by this choice between I and j. So guess what? We'll need to do some pattern matching on that. Right. If the variable says an element goes here, so that's the in left choice from I plus j, and it is of sort I, then we know.
That's element.
Sorry?
That's element, so we turn on.
Yeah, it's an element, not a subtree. So that means we've got to use x to interpret the I. If, on the other hand, we are asked for a subtree, that's where we get to use the data type recursively. And remarkably, Agda's happy. So let us indeed make sure that we can build vectors this way. So we've got to figure out what's going on with this. What's the thing that plays the role of f to make vectors? What are the sorts of vectors? They're given by how long the vector is. And what are the sorts of stuff inside a vector? Well, they are either elements of the vector or subvectors that have a particular length. We get to see the length of the vector that we want to build, and it even makes sense to look at that length in order to say how one would build a vector. So, what polynomial characterizes the vectors of length 0? The constant 1. And what polynomial characterizes the vectors of length suc n? What does a cons look like? Well, step 1, it's a pair of a head and a tail. Right. What sort of thing is the head? It's an element. So we're certainly going to have to give a variable or quote. What have I done? And then we have to say, so now we're being asked, element or substructure? And we just said, it's an element. What about the tail? That's recursive, so it's doing the, well, I'm making the same mistake twice. So we've got another position for stuff, but this time the stuff isn't an element, it's a substructure. And that means we have to say how long we would like it to be. So we give n. Okay, so that gives us the form of a vector, and we can, well, let's just check that we can build the usual stuff for vectors. Let's have define v nil. Let's see what happens. What's v nil going to be like? Well, it's certainly going to be a node of a tree. And then let's see what we're asked for. Oh, good. We're asked for something rather boring. So just as we said, empty vectors are characterized by the polynomial 1. So when we try and build one, we just have to give inside. So that the outer angle brackets build a node, and inside we're just asked for an element of 1. If we want to build the cons, then I better make these capital Vex. You will not be surprised to learn that a cons is certainly a node. And now what are we asked for? We're asked for a pair, because that's what we said we ought to give. And in the head position, we're asked for something of the element type. And in the tail position, we are asked for a vectory thing with index n instead of suc n, so we can fit in our x's. So we have taken our old hardwired data type of vectors and turned it into a piece of software, right? We've now actually got, red data that tells us how to build this data structure. We've taken a hardwired language feature and turned it into essentially a data type of formats, and we can express the same stuff. One thing you might hope, and it's a good thing to hope, you spent a while showing that that vectors behave like a functor, right? That they pack up elements, and if you've got an operation that acts on the elements, you can do that operation to the structures. That's one thing that's worth doing. So let's see if we can explain how to write the generic map operation. So grab all of these bits and pieces. Suppose we have two different sorts of data, x and y, and we have a function which offers to turn x's into y's. So this says, for each sort of element, we have a function that turns x's of that sort into y's of that sort. Then we ought to be able to turn, for any data structure given by a polynomial, we ought to be able to traverse the whole structure and turn the x's into y's. So we're basically looking for the element position because that's where we're going to do some work. So what's going to happen? What have I done? I've forgotten an arrow. Right. So what happens here? We have, well, we know our data will be made by a node. So what have we actually got? We've got one of these structures. And now, I've got a feeling that a while ago I implemented map for polynomials. Why? Yes, I did. It's even called eval. What does it want? It wants, two sorts of thing.
let's see how lazy I can get away with being. I'm certainly going to need to get my hands on f here. And I hope I'm going to be able to get away with underscores there. The polynomial we're working with, as you can see, is f of j. Don't know what the function is yet. Do know that that my data is x of t. What have I? Oh, forgot to rewrap the output. Okay. So I know what's going to go wrong any minute now. But you can see, what are we being asked for? We're basically saying, we already know that all of our polynomials are functors. So now we have to say why this structure that's built from polynomials is a functor. And we can work one node at a time. And we have to say just what to do when we hit a variable. And look, the variable says what's here is either an element or a substructure. So we're going to have to look at whether we're at an element or a substructure. So we've either got an I or a j, and we need an extra set of parentheses around that lot. Okay. So, in the left case, we're looking at an element. We've got a function that says what to do on elements. And this is where our luck runs out. If we have a substructure, what would we like to do? We'd like to map recursively. So we hope we can get away with saying gmap fj, and then the termination checker kicks us where we don't enjoy it, because it can't see why this map operator will use our recursive function only on substructures of the original. So that's a source of frustration, but the cure is relatively straightforward. We retreat. We say, okay, we know at least we're going to turn a node structure into another node structure. So there's going to have to be a helper function which gets handed f of j, f and xt. We're awfully lucky. Yep, that looks about right.
Is there a particular reason you're not using where in this case?
What went wrong there? I could use where if I wanted to prove properties about this function, like that it satisfies the functor laws. I would probably, it would be cleaner if it's at the top level. So I'm writing it as a mutual recursion at the top level rather than as a subordinate helper function. But yeah, you you certainly could write it as a where, and then you would need less abstraction over all of this stuff. Now, where did I go wrong? Shows the benefits of rehearsal. And I see. I'm going to need to make that explicit apart from anything else. And I'm still right. And now we've got so why is it that wasn't very helpful of it. Where am I screwing up? XT is supposed to be that's entertaining. I think I know what's going on. It's saying that these two things are different. And when they look pretty similar, the only thing that you can see that's different is that this one just says y, whereas this one says the function that takes an argument z and applies y to it. Those are, as far as AGDA is concerned, those are the same function. So AGDA is telling me that two functions which are actually the same are different, and it's right. I wasn't expecting that when I woke up this morning. Why are they different? Because each of these lambdas is behind the scenes implemented by a different helper function. When you write a pattern matching lambda in AGDA, AGDA behind the scenes writes a helper function that does pattern matching, and it's saying, and it's just comparing. It's generating two different helper functions, one for each lambda, and then it's just saying, oh, those are different functions. They're not the same implementation, even though, I mean, they are not the same definition, even though the functions are defined in the same way. It's not comparing the actual definitions, it's just comparing the names that it's generated and saying, oh, those are not the same thing. So some intimidation may be necessary. To do that, I will write the helper function that it's actually generating. So that's an interesting gotcha. Now let's see if I'll get away with this. Right. And now this should say and it can see that choose is the same as choose. There's now only one definition. So we have successfully intimidated the thing into submission. It's confused about a missing J. Why? Shouldn't be. Let's just get rid of that. It's not relevant. Okay. So we've managed to build our helper function, or build the main thing by introducing a helper function. What went wrong? Agda didn't like two pattern matching lambdas, even though they said the same thing. It wouldn't admit that they were equal, so I pulled them out as a proper top level definition, and now there's only one thing. We're ready to go. The usual thing has happened in these situations. We saw this before. We still have our general purpose f that tells us what all the node structures are, but now we locally have a p polynomial which tells us just the structure of the node that we're working on. And then when we pattern match on p, f stays the same. So we saw that before. We'll see it again. So what happens here? We find a variable. We need to know, is it an element or is it a subnode? If the choice goes to the left, it's an element of sort I, so we can do f to it. If it's a subnode, we can call gmap recursively. And this time, the termination checker does not howl. If the polynomial is a constant, we don't care which constant, we can just give the value straight back. And it's the usual story. If the polynomial is a sum, then we have to see whether it's a lefty or a righty. And of course, we have to put the same thing back. And depending on whether it's a lefty or a righty, we have to do the appropriate recursive call to it. Meanwhile, if the polynomial is a pair, we've got two substructures. And we have to give back a pair. So we have successfully intimidated the termination checker into believing us at the cost of having to inline a perfectly respectable general purpose map function to the special case of the operation we're defining. We also had to fight the type checker a bit, but we have written all the maps, right? So you see when you implement a map operator for a particular data structure, you ought to have a certain kind of sense of irritation that you are doing a computer's work, and if you're, that's something you should feel entitled to be unhappy about. If you are doing a computer's work, what we've managed to do here is get a computer to do a computer's work. We feed in as data the description of our data structure, and out comes the implementation of a handy general purpose piece of equipment, the map operator for that data structure. And all we had to do was say, you know, here's where the elements go and what sort they are, here's where the substructures go and what sort they are, and then that information is enough for us to work our way, preserving all of the constructors, but when we reach a position for some actual data, is it an element or a substructure? Well, in both cases, we know what to do. This is the power of what you can do when you move away from data structures being hardwired things declared with data declarations, like you know, hey, I just had this wonderful idea for a data type. I wonder if that data type has any structure. To something where the structure is something that you can show exists once for all. So we're still in a sort of transient state here with dependently typed programming, where on the one hand, we can do this sort of thing, but on the other hand, the data we end up working with look kind of fairly inscrutable. You know, if you use these encoded data, then all your stuff looks like angle brackets and empty tuples and commas and in lefts and in rights. You can't read your programs anymore. On the other hand, you can use power tools to generate those programs. So the designers of dependently typed languages we haven't really got our heads around how to exploit this possibility to encode data structures in software within our own languages. That's we're still giving good support to kind of hardwired data types declared with the data construct, and we have an awkward time working with encoded data structures. So I don't know, maybe in future, I certainly hope we'll get to a stage where when you write a data declaration, what should really be going on, what it should really do when you write a data declaration is generate the code that describes the data type and plug it in to a construction like the one we've seen here. So when you write, when you declare the vectors using a data declaration, it should actually generate this stuff. There's no reason why a machine couldn't do that. And what's more, it should use the availability of type information when you see vectors and pattern match on them and things like that to show you the data in the form that you asked for it, even though behind the scenes it's encoded just in terms of sums and products. So we don't yet have the best of both worlds, but we are at the beginning of a technology that's really rather powerful. Okay, that seems like a good place to stop for the day, unless there's anything you want to ask me, either about this material or about exercises or stuff. And we should also probably, I don't know, how's exercise 2 going? I mean, is it, if it's going well, you should, or rather, if you're battling through it and winning eventually, then we should probably have some feedback time. If it's causing difficulties, we should probably identify what they are. Because I'd be keen to shift it. But we're not in a state of underflow, right? Or are we? Good. Well, I will put some more stuff in the pipe. Hopefully, I've got a long train journey tomorrow. That's always good for running programs. Okay.